I'd like to welcome everyone to the Blue Box 2021 webinar series. My name is Bill Eggers. I am the president and owner of BioLogic USA. The following presentation will last for about 40 minutes and will be followed by a short Q&A session. You'll be able to enter your questions through the GoToWebinar portal that should be on your screen during the presentation, and you can enter these questions as we go. The presenter will address the questions following the presentation. Our speaker today is Professor Shannon Boettcher. Shannon is a professor in the Department of Chemistry and Biochemistry and the Material Science Institute at the University of Oregon. And I don't know if I'm saying Oregon right, but he'll correct me later, I'm sure. In addition, he is also the director of the Oregon Center for Electrochemistry. He is also an ONAMI signature researcher, which stands for the Oregon Nanoscience and Microtechnologies Institute. I have known Shannon for many years during his time at the University of California, Santa Barbara, and then at Caltech prior to his appointment at the University of Oregon. At my last count, he's published about 89 papers. Professor Boettcher today will present his work on advanced bipolar membranes, covering design principles and applications in electrochemical technology. You can reference his full abstract that was included on the announcement for this webinar. With that, I give you Professor Boettcher. Shannon?
Welcome. Thanks everyone for coming. Let me share my screen. I'm excited to tell you about a little bit of the work that we've been doing here at Oregon. Let's see. Let me have to choose what screen to share. Sharing. There we go. Okay, so you should now be seeing my screen. Please let me know, organizers, if it's not coming through. So I'm excited to tell you a little bit about our work in advanced bipolar membranes, and I'll tell you what these are and how they work, and I hope to finish this up with a nice conversation with folks who are online who have questions, and that should be a lot of fun. So you know, everybody knows in an electrochemical cell, right? The key component, one of the key components in every electrochemical cell is the electrolyte. And, you know, typically, if you go back, right, there's a salt electrolyte, aqueous batteries, or in plating solutions and in water. This is the voltaic pile, originally developed by Volta, right, in the 18th century. Fuel cells, PEM fuel cells, PEM electrolyzers, you have acidic membrane, alkaline electrolysis, you might have concentrated KOH. In each of these types of systems, you know, you typically have an electrolyte that is uniform in composition. In water, that means it's operating at a single pH. Now, what if you could free yourself from that constriction? What if one wasn't restricted to performing electrochemistry in a single electrolyte or even at a single pH? Now, there are, of course, ways to do this, and one of those is called a bipolar membrane. That's what I'm going to tell you about today. And a bipolar membrane is quite a simple construction, though the physics of how it operates are still not fully understood. So a bipolar membrane is constructed by taking an alkaline membrane, so something with fixed cations and mobile anions, in this case mobile hydroxide, and laminating it with an acidic membrane that has mobile protons and fixed anions. When you do this, you have essentially an anion conductor and a cation conductor laminated together, so it acts sort of like a diode does in electronics, a PN junction diode. Now, these have been known for a long time, over 50 years. This is the first paper that I know of reporting bipolar membranes. So what can you do with these? So I'm going to review a few of the exciting applications people are thinking about. So one area is in electrolysis. Okay, now there's no commercial applications in electrolysis yet, but one could imagine that you could build an electrolyzer. In fact, we've done this, and I'll show you some of that data, where you have one side, for example, the cathode in acid, and the other side, the anode in alkali. Now, why would you want to do that? Well, the hydrogen evolution reaction is fast in acid, and the water oxidation reaction can be fast with non-precious metals and alkali. So this allows you another knob to optimize an electrolysis process. So how does this work? How do you maintain acid and base in an electrochemical cell at steady state? Why don't they just neutralize? Well, they want to neutralize, and they will try to neutralize at some slow rate. But if you think about the bipolar membrane, and we'll get into the details of this, if I zoom into this bipolar membrane, and this is from a nice paper by Vermaas, now a professor at Delft, the Netherlands. Say I have a cation and I want to pass positive current across this membrane. Say I'm a cation and I want to pass positive current across this membrane. Now the cation is not very conductive in this anion membrane. All this positive fixed charge keeps the cations out by Dohn and exclusion. So this membrane primarily conducts hydroxide. So I can't get positive charge across from right to left here via this mechanism. I can, however, diffuse in neutral water and then right at this interface, dissociate that water into protons and hydroxides and shuttle those selectively out in both directions. So the key concept here in a bipolar membrane is that in order to pass current, steady state current across the membrane, I either need to make hydroxides and protons at the junction and push them out, or we call that reverse bias, or in forward bias, I have to recombine them and make water in the middle. So one ion does not move through the junction predominantly. It's neutral species that are either being ionized or recombining in the middle. So in this way, you can maintain a steady state acidic and alkaline environment as you consume protons at your cathode, consume hydroxide at your anode, but make them in the middle. There is historically many applications for these, and some of these are commercialized, particularly in electrodialysis. So this is a very developed technology. You can take a salt solution, say it's sodium chloride. I can take an anion and cation selective membrane. I can move the cations through this way through the membrane by sourcing current between an anode and a cathode, and these are usually stacked together, repeating sort of 50 times or something like that. Then I can have another stream coupled to a bipolar membrane where I flow pure water in. It collects the anions and the protons and makes acid. The other side will collect the hydroxides and the cations from the other side of the bipolar membrane in the stack, and it makes base. So this is a way to actually make acid and base, to synthesize acid and base electrochemically. Now you can use that acid and base for all sorts of things. There are lots of applications in precipitating impurities in water. So for water purification, you might want to make acid and base on site. You could desalinate that way. The salt stream becomes desalinated. You can collect and recycle impurities. For example, if you have a production process and you want to collect some cation. There's some emerging applications for these that are quite interesting. So we hear a lot about CO2 capture and negative emissions. The challenge is, how do you take the CO2 and separate and concentrate it? So one strategy is to collect the CO2 in strong base, reacts spontaneously with strong base. Then you have carbonate. And so bipolar membranes can be used to collect carbonate from those basic streams, acidify the carbonate, generating CO2. And there's a number of pure CO2 that can be then collected and used for downstream applications. And there's a number of technology ideas that use these bipolar membranes in this type of context. Here's another key application that's emerging in the last couple years. So there's a lot of interest in taking carbon dioxide such that you might capture in the process I described previously and electrolyzing it to make reduced products, whether those are fuels or chemicals. Here's an example of the type of architectures folks are designing. This happens to be from a nice science paper by Ted Sargent's group. And in this case, they've used an alkaline exchange membrane to separate their anode and cathode chamber. And they can make reduced carbon products at very high current densities over an amp per centimeter squared. The challenge, one of the challenges, there's a number of challenges in these types of technologies which are being addressed, but one of the key challenges pointed out by Brian Seeger and others is that when you have a monopolar membrane separating your anode and cathode, in this case it's an AEM, an alkaline exchange membrane, the CO2 on the cathode side rapidly reacts in this basic condition to form a number of species here, carbonate species. Those are negatively charged and those will get carried across the membrane. If you make negatively charged species like formate as a product, those will also get carried across the membrane. So for every electron you pass here, you need to move a negative charge. And so you can lose substantial quantities of your CO2 due to this crossover. And that's a huge loss and hit in the efficiency. This CO2 is then re-emitted mixed with your oxygen at your anode side of your cell. So how can we solve this? Well, another key advantage of bipolar membranes, and this is shown in this nice paper by Tom Malouk's group, from Tom Malouk's group. A bipolar membrane has predominant ion flow out from the center of the bipolar membrane, because that's where you're dissociating water. That predominant ion flow out dramatically retards the crossover of reactants and products from the cathode. And so in a CO2 electrolysis system, if you could use a bipolar membrane, if you do use a bipolar membrane, you have dramatic reductions in crossover. Okay, so if these BPMs are so useful, why are they not used everywhere? And so this is Sebastian Ohner. He's now a group leader at the Fritz Haber Institute in Berlin. And he did a lot of the work I'm going to tell you about here. And this is one of the questions we tried to answer. So one of the challenges, actually, is that the performance of the bipolar membranes, I'm going to talk about sort of voltage or energy efficiency, though that's just one metric. Of course, durability, crossover of unwanted species, other things like that are also important. I won't talk too much about that, though we can talk about that in the question and answer section if you would like. The efficiency of these bipolar membranes is not particularly good. So this is a paper, really nice paper from Peter Pintaro. Tom Malouk is involved in some of this work as well. And they show here data first for a commercial sort of standard bipolar membrane. This is what most of the academics use because you can buy it from Fumatech easily from the fuel cell store in small quantities. And this black curve here, you see this voltage here, this is sort of the equilibrium potential. We'll talk about what that means in a moment. And then, as you know, in electrochemistry, we have overpotentials that are required to drive any rate process. And this process is going to be associated with water dissociation. So this is going to be eta water dissociation. And you can see to say drive 100 milliamps of current through the bipolar membrane. There's about half a volt actually for the Fumatech membrane, over 700 millivolts of loss. At a fairly small current density, you're paying 700 millivolts to dissociate that water to make that acid and base. Okay, so that's a problem. If you want to make an electrolyzer that runs at 1 amp per centimeter squared, right, then this is not possible. Simply not viable approach. Now, what Peter and his group did, and it's a brilliant study, they used electrospinning to make three-dimensional junctions between the cation and anion polymer. And what that does is it gives you more surface area over which to dissociate the water. And they were able to reduce this substantially and get to higher current densities. They took some of these out to 1 amp, but there still are large losses, okay? There's still large losses here that are really not acceptable for any sort of energy technology. Now, if you're doing recycling or electrodialysis and you don't care that much about the energy efficiency of your process, it's okay. But when you talk about energy technologies, the energy efficiency is really important. Okay, so let's think about this. Where does this come from? So here's the freshman chemistry of water dissociation. So everybody knows that water auto dissociates into protons and hydroxides. We can give it a forward and a backwards rate constant. The equilibrium constant is the ratio of those two. We know from groundbreaking work of Eigen and Erdl that the recombination process is in fact one of the fastest chemical reactions known. And so we can calculate from this ratio the forward rate constant. So the backwards rate constant is fast, 10 to the 11th. That's the recombination rate constant. It's almost very small barrier in free water for that. And so from this, you can calculate that, the forward rate constant is actually quite slow in bulk water. So on average, a given water molecule will dissociate every 10 hours at 25 degrees C. So, part of the reason the kinetics are slow is that this bulk water process, part of the reason there's a large overpotential is that this process is slow. So we need to understand it better and understand how to speed it up. That's one of the things we're trying to do. So what happens in a bipolar membrane junction? So here's a sort of simplified picture. We'll dive in a little bit deeper in a moment. So if I have an alkaline membrane and a cation membrane, of course, if I bring the two together, there'll be some partial transfer of protons from the acidic side to the basic side, leading to partial neutralization. Now, remember, though, that there are these fixed charges, these sulfonic acid groups, for example, in Naphion, these quaternary amine groups in an alkaline membrane, and they leave behind fixed charge. This is the charge density here, much like a PN junction in semiconductor physics. Now, this fixed charge leads to an electric field across the interface. Here's the electric field profile, and thus an electrostatic potential. Okay, so we need to understand that, and here I've actually drawn a region, okay, over which there's a gap between the two membranes, and what we're going to do is we're going to put stuff in this gap. We're going to put particles in there, and in fact, we're going to use oxide particles primarily, and I'll show you why in a moment, and study how that affects the rate of dissociating water. And we need to keep in our head what's going on here. Now I'm going to go through this a little bit quickly, but the sort of underlying physics is fairly simple. So we often use concepts of the electrochemical potential, which is the total free energy of, say, a proton or a hydroxide. Now at equilibrium, that has to be flat, has to be equal everywhere across the junction. And it can be equal because the concentration gradients, the free energy due to concentration gradients are balanced by the free energy due to changes in electrostatic potential. Okay? And then when we apply a voltage and we try to pass current from anode to cathode, we have losses due to water dissociation that gives rise to a gradient in the electrochemical potential of, say, protons or of hydroxides. And that's this overpotential that we're measuring. It's that gradient across this interface, and that gradient in free energy is ripping apart the water and creating protons and hydroxides and separating them. Okay, so that's what we're going to measure. And how we measure it, there's a number of ways. The classical way is this. You take two compartments, one with a strong base, one with a strong acid, or two electrolytes of known pH, and you put in those two compartments two reference electrodes. We're going to use identical silver chlorides, but you could use other reference electrodes as well. And our bipolar membrane is right in the middle. Now, the electrochemical potential of protons, this is the definition. It has a standard term, has an activity, a concentration term, and it has this term depends on electrostatic potential. So from the equilibrium condition, we know that this has to be the same on both sides, even though the pH is different, the electrochemical potential has to be the same, and that gives rise to an equilibrium electrostatic potential across this junction. So there's a Nernstian electrostatic potential, that's this difference in phi, across this junction at equilibrium. Now, when we go away from equilibrium, we're going to perturb that electrostatic potential, and we're actually going to measure it with these two silver chloride electrodes. And I won't go through this, but you can convince yourself that the junction potential can be measured directly by the difference in the voltage across those two references. Okay, so here's some data from the literature for water dissociation overpotential. So without catalyst, you get these huge voltages to drive water dissociation at very small currents. And here's these sort of commercial membranes, the Fumatech and others, that are about 100 to 200 millivolts at a small current here of 20 milliamps per centimeter squared. And others have looked at graphene oxide. It's a nice processable material that can be used to catalyze this reaction. It has sort of similar performance to the commercial. And again, these are much too high over potentials to use in energy technology. So how do we get this lower? So we started to make our own bipolar membranes. We took Nafion, we spray coated nanoparticle catalyst, we put an alkaline ionomer on it, and then we added a distinct AEL membrane layer and made a sandwich, pressed it together. And we tested this in a number of ways, and one of the innovations that was important turned out to be extremely simple. So traditionally, folks have used these sort of H-cell environments. And one of the problems is when you put stuff in the middle of the two membranes, they don't adhere well to each other all the time. And often additives and glues are added, or some sort of polymer adhesives are added to keep those membranes from de-adhering under current flow. But we have another program in our lab looking at MEA water electrolysis, membrane electrode assembly, where the whole thing is compressed inside of a standard MEA electrolyzer. And we thought, well, let's test the bipolar membranes in an architecture that is similar to what you would use in an electrolyzer or an MEA fuel cell. And what's nice about this is it keeps the bipolar membrane under static compression. Okay. And so the challenge with this, though, is that we can't easily, though we kind of work out how to do this now, you can't easily integrate reference electrodes into this sort of MEA environment. So we actually made two different types of measurements. We made the MEAs. We put catalyst on both sides with our bipolar membrane, and we tested it either under compression in the H cell, where we have KOH and sulfuric acid on either side. We also tested it in this pure water electrolysis system, where we actually don't have any free electrolyte. This also simplifies the measurement because we don't have to worry about crossover of these free electrolytes. Okay. So what we do is make a current voltage curve. Here is for the MEA water electrolysis system. And we measure, for example, the total voltage to drive some current. In this case, we're also not only dissociating water, we are paying the price for making hydrogen and oxygen. We're paying the price for driving the water oxidation kinetics and other kinetic processes. So we can assign roughly the water dissociation to this sort of difference between what we expect and what we get. And we'll go into this in more detail and quantify this water dissociation over potential. And to start with, we looked at a number of different catalysts that are common in the literature, and we found things like iridium oxide and nanoparticulate TiO2 anatase, particularly, to have fairly good performance, actually, fairly similar to some of the best stuff out there when tested in this type of environment. So this piqued our interest in looking at these sort of nano oxides. Now, we want to get more quantitative data. So what Sebastian did is he measured now in the H cell, where you have these two reference electrodes, you can get the equilibrium potential. It's about 830 millivolts. That's the equilibrium electrostatic potential across the junction. And then you can apply current and see how the equilibrium potential changes. And from that, you can get very accurate measurements of the water dissociation over potential. Then he can take this exact same membrane electrode assembly and test it in the water electrolyzer, the pure water electrolyzer, where you don't have this acid and base, strong acid and strong base, which can cause some problems for some of the catalysts we're looking at, and measured this light green curve. Now, this curve also includes all the water oxidation, water reduction kinetics, and overpotentials, so we can subtract the water dissociation overpotential to get a baseline data for how well this electrolyzer would perform if water dissociation was perfect. And then we can use this baseline. This is baseline for a simple iridium oxide catalyst, which is very stable. We can test other catalysts relative to it. And now we can use two electrode geometry and get quantitative values for water dissociation. Okay, so how do we think about designing catalysts for this process now that we have sort of a platform that we think we understand? Well, one thing we thought about, the alkaline membrane and the cationic membrane when they're brought in contact and there's this sort of region in the middle, which we're going to put catalyst, we spray catalyst. If you think about what the pH is, the pH is actually not constant with position. You have a strong base on the left, strong acid on the right, and so there's going to be a gradient in pH going from 14 to 0, roughly, across this junction. Now, why is that important? Well, if I think about this process of making protons and hydroxides from water, that process is going to depend likely on the local pH if it's mediated by the surfaces of the catalytic particles we're putting in there. So consider oxides. So oxides, right? A metal oxide surface typically has hydroxyl groups. These hydroxyl groups can be protonated, they can be unprotonated. And on average, we can measure the charge on a particle, and we can represent that as a zeta potential, and we can measure that as a function of pH. And what you find, of course, is that different metal oxides have different pHs on which, on average, the surface is neutral. And this is because the acidity or basicity of these different nano oxides are different. They have different chemistries. So some are basic oxides and some are acidic oxides. And the pH substantially affects the surface chemistry. So if you took a basic oxide and put it in a locally acidic condition, it would be highly positively charged as all these sites are protonated. We'd expect that to affect how these do water dissociation. So there are some mechanisms in the literature going back to Simons, a couple of beautiful papers talking about how protonation, deprotonation steps can catalyze potentially this water dissociation. So here's an example. Imagine I have a oxide surface, and that oxide surface has some deprotonated and some protonated hydroxyl groups on it, and say this is under basic conditions. So it's sort of a little bit basic of the pH of 0 charge. The protonated site could donate a proton to water, giving rise to a hydronium cation and a deprotonated site. That deprotonated site or another site that is deprotonated on the surface could give rise to a hydroxide. Now, this is now a two-step mechanism by which the net product is dissociated water, acid and base, and the MOH and MO minus are the catalytic sites that are driving that proton transfer reaction. So in order for this reaction to be fast, though, you need both deprotonated and protonated sites. So you need a good mixture of these because you need both steps to be fast. Now, in acidic conditions, I could write a similar mechanism, but using a protonated hydroxyl and an unprotonated hydroxyl. So we have this hypothesis that the catalyst should dissociate water best when you have a mixture of either these two sites or these two sites. And that's going to happen when you're not too far from the point of 0 charge, because both steps must be fast. So in order to test this hypothesis, Sebastian did a very nice experiment. He took bipolar membrane and he put two different types of water dissociation catalysts. So we're going to put oxides of one type on the alkaline membrane and then oxides of another type on the cation membrane to represent the fact that one local condition is acidic and the other is basic. And here's some of the results. So what Sebastian did is he chose a stable catalyst. This happened to be antimony doped tin oxide nanoparticles, just commercial particles we put off the shelf. They're very acid stable. Put them on contact with the acidic Nafion membrane, and then systematically changed the catalyst we put on contact with the alkaline membrane. And what you see is that the catalysts that perform the best with the lowest overpotential for dissociating water are actually alkaline oxides, things with alkaline points of 0 charge. And there's roughly a correlation here, though there are some outliers, and we have some hypotheses in our understanding this, but generally the best catalysts have a basic point of 0 charge. Those work best in the basic local environment. And that's consistent with the sort of simple mechanism, 0th order mechanism we put forward. Now you can do the same thing. You can put nickel oxide, which is a basic oxide, stable on the alkaline surface. You can put other oxides on the acidic surface. And again, you find the best materials that have the lowest overpotentials are acidic oxides in contact with the acidic surface. And now you find that some of these bilayers with nickel oxide on the basic side and optimized catalysts on the other side, they have overpotentials that are approaching zero, within error of 0 millivolts at this small current density of 20 milliamps per centimeter squared. Now, this is much smaller than historically has been achieved by these materials. So this is, almost a 10x improvement in bipolar membrane performance, at least on this one performance metric. Now, of course, there are a lot of other performance metrics. If there's any bipolar membrane manufacturers out there, they know, right, that this is not the only thing you care about. But it's one thing that's important to think about, and we're trying to understand it from a fundamental perspective. So we published this paper. One of the reviewers asked us to show an electrolyzer operating at high current density, because that's one of the things we said we should be able to do with this. So we built one, and we have better ones now, but this is what's published. Here's a bipolar membrane device. It's this red curve here. Here's the total voltage, again, to electrolyze water as a function of the current density going out to almost an amp per centimeter squared. The black is a not state of the art, but decent proton exchange membrane electrolyzer that we built in our lab using all the same processes, same membrane, same catalysts as we used in the bipolar membrane electrolyzer. And then the blue is an alkaline exchange membrane electrolyzer. Now, these are all electrolyzing pure water. There's no salt in the electrolyte, no acid, no base in the electrolyte. And the blue curve is an alkaline exchange membrane electrolyzer. And this gap between the alkaline and acidic membrane electrolyzers, this is well known. You can make better alkaline exchange membrane electrolyzers using some advanced polymers, which we're doing now. But the key is that everything among these three systems are identical. And what you'll notice, and this was to me quite remarkable and proof of what I've been trying to argue about the performance of these bipolar membranes, is that we can take the AEM system, the alkaline exchange membrane system, we can add a cation membrane and water dissociation catalyst. We just add a bunch of stuff to this electrolyzer, yet the performance is essentially identical. In fact, it's even better at low current densities than the alkaline membrane electrolyzer. And the reason it can do this is because in an alkaline exchange membrane electrolyzer, essentially you're doing HER under basic conditions. You're essentially getting your protons from water. You're dissociating water at the HER catalyst. Now we've moved that water dissociation step to an optimized catalyst layer, driving only that reaction at the bipolar junction, and we can make hydrogen fast in the locally acidic environments. And this is not nearly optimized. There's a lot of things yet we can do, including making 3D junctions like this work from Bintaro. Okay, so what other things have we been working on? So one of the things Sebastian noticed, and this is in the literature, I should have the original reference to some of these studies, but what's been noted is that as you go to high current density, because the anion and cation motion is out from the center of the junction, the water is dragged out of this cell. And that's a problem, right? So this inner layer here is going to dehydrate as you lose water, as it's dragged out, as water is a hydration of these ions. And so water needs to diffuse back in to replenish that water so it can be dissociated. And what that leads to at high current densities, it leads to an increase in overpotential as the junction dries out. Now, what Sebastian showed nicely, and he made a bipolar membrane electrolyzer with very thin cationic layer here. And this cationic layer is only about 2 microns thin. You can see it sort of sandwiched in this cross-section device here with a thicker AEM and a little bit of water dissociation catalyst in the middle. And when you do this, you can drive these bipolar membranes out to very high current densities, out to 4 amps per centimeter squared. And notice the huge difference when you don't have a catalyst to when you do have a catalyst. No catalyst, you essentially can't drive any current through these devices. These are really good diodes, right? They don't allow you to drive current through them. And it's only when you catalyze the dissociation process that you break down essentially the diode, and it'll allow you to pass these huge currents. Okay, so this is exciting. So one of the things we're working on now, I won't talk about any of the data, but we're thinking about using these in sort of dirty water or seawater electrolysis. That's one of the applications the Office of Naval Research is interested in, where you can control, for example, chloride crossover and other impurity crossover for generating oxygen, for example, for life support, things like that. Okay, so I want to end here with a few more points of what we've been doing recently to think about, what are the other factors that drive performance optimization and sort of underlie the fundamental understanding of how these bipolar membranes work. So, one obvious question is, what is the thickness of the layer of catalyst you put there? And it turns out it's not an easy question to answer. Roughly, we get the best performance from a few hundred nanometers. Okay, so this is a control, very well-defined system where we have TiO2, anatase primarily. I think this is P25, commercial Degussa catalyst. And we look at the loading dependence of the total water dissociation or total electrolysis voltage, actually. Okay. And you can see sort of for even up about 500 milliamps per centimeter squared, you get to about 500 nanometers of oxide nanoparticulate in the junction, and you get actually about 2 volts total voltage. So that's actually quite good for a bipolar membrane electrolyzer. But then you put more on, and it gets worse. Okay, so why is more catalyst not better? So that's one of the things how Kuhn has been working on, and the answer is actually very simple. We put together just a toy model, a finite element simulation of a bipolar membrane. Doesn't have all the physics in there, but we think it's good enough to understand these types of phenomena. And these different color curves are different activities of the catalyst. And what this shows is, again, an optimal sort of catalyst layer thickness. So why is that? Well, at low thicknesses, you don't have enough sites to drive water dissociation. But at high thicknesses, you start becoming limited by the ohmic losses, in fact, in this junction region, because you have to move the hydroxides and protons out from the center. And when the thickness is large, that drop in electrochemical potential is not as sharp. So the driving force for pulling those apart becomes smaller locally. So there's an optimal thickness there. And so we've been working to understand that quantitatively and apply that to these more complicated bilayers and multi-layer catalyst systems. The other thing that's interesting is if you look at some of the details in some of this data, you'll notice that things like rutile TiO2 and anatase TiO2, even though they're very similar in chemistry and similar in size, actually have quite different overpotentials. When I put anatase in there, it's close to 0 or 20 or 30 millivolts on this scale, and this one's more like 60, right? So there's a big difference there, over a factor of 2, and they don't trend in the sort of way our global, rough trends do. There's of course a lot of noise here, but the anatase is a little bit more basic than the rutile. So why is this? So what we've been doing is, again, an obvious experiment, but we need to do it carefully. It's not actually that trivial to get good data, where we look very carefully at the proton consumption functions. This is essentially a pH titration of the hydroxyl groups on the bipolar, on the catalyst that we use in the bipolar membrane. And what you see is that anatase has a much higher density of hydroxyl groups, or maybe we should not even call these hydroxyl groups. We don't know their chemical nature. We just know of absorption sites for protons than rutile does. So we think anatase has simply more active sites for doing proton transfer. So we're trying to sort all this out now. Okay, so I only have a minute or so left, and I wanted to, generally talk about these concepts of water dissociation catalysis. So we expect these to be general to other phenomena. So what's an example of that? Well, if you want to make hydrogen in base, and I already alluded to this, you actually need to get your protons from water. So if I want to make hydrogen in alkaline conditions, I don't have any free protons like I do in acid. So I actually need to dissociate water to do that. at the electrode. So now I'm, talking about electrode reaction. It's also true for CO2 reduction. So this has been known for a long time, and in fact, there's some beautiful work from Nemanja Danilovic, Nida Markovic, and many others showing that you could actually speed up the rate of hydrogen evolution on platinum if you modify the surface with catalysts that in some way speed up this water dissociation step. And so one of the things we want to do with our bipolar membranes, one of the science aspects we're interested in is can we use them to understand this type of data? And so what Sebastian did, I'll show this real quickly, is he went and bought a bunch of precious metal catalysts from the fuel cell store of different compositions. He measured how good they dissociate water in the bipolar membrane, and he compared it to how well they drive the hydrogen evolution reaction in basic conditions. And look, there's a linear correlation between the two. That tells us that this concept of water dissociation here and water dissociation at electrode surface driving hydrogen evolution reaction, they're somehow correlated. You do the same measurement in acid, of course, it doesn't matter because you have lots of free protons, you don't have to dissociate water. So Sebastian did a few other things. He took a catalyst, for example, that wasn't that good at making hydrogen and base precious metal catalyst, and you modified it with some titanium dioxide, which is highly stable water dissociation catalyst. It's stable in acid and base, and look, it gets much better. And this is consistent with all the Markovic work. You can actually speed up the electrocatalysis by covering some of the active sites with titanium dioxide by allowing the water dissociation reaction to go faster. And of course, it doesn't matter in acid because you're not doing water dissociation. And so Sebastian, being a very hardworking and productive postdoc, measured every single precious metal catalyst with different amounts of TiO2 on the surface, and they all fall in this line. If you make water dissociation better in base, you make it better for driving HER as well. So this sort of shows the sort of underlying fundamentals of how these concepts connect across and through electrochemistry. Okay, so I want to end there. I have a few more announcement slides. So, we think this is an important concept in thinking about this. We don't think we understand it all yet, but we're making progress. We are working on design principles for making these better. We're working on applications with a number of collaborators. We have a lot of interest in understanding really the physical picture at a greater level of detail. I want to highlight Shane Ardo. He's done a lot in sort of thinking about bipolar membranes in various contexts, and we work with him and talk to him about some of this stuff, and that's been really helpful. So, I mentioned we're here at the Oregon Center for Electrochemistry. So this is a new initiative I started last year. I encourage you to go to this site. If you're interested in learning electrochemistry, I'm actually posting quite a few videos on core electrochemistry concepts from my electrochemistry lecture series and electrochemical engineering and fundamental electrochemistry here. You can watch those for free and other things here. We also have a new program, a new graduate program in electrochemistry, a master's internship program. And this program is really unique. It's the only one in the nation that focuses on electrochemistry. It's 6 months of coursework followed by an internship. It's quite popular. We're working with a lot of companies. So if anybody's interested in hosting interns or hiring out of this program, please contact me. If students interested, please send them my way. So with there, I'll end. Thank you so much for your time, and I'll turn it back over to Bill.
Well, thank you very much, Professor Betcher. I'm going to introduce one of our staff, Dr. Arnold Foreman, who's been monitoring the questions and the questions that we're going to try to provide some answers for. And he'll take us through the next 15 minutes or so where we can get some of the questions presented to Shannon, and we'll see if we can cover those in the short period of time that we have left. So, Arnold, I'll turn it over to you.
Thank you, Bill. Can everybody hear me? Okay,
Yes.
Great. Just a reminder, if you have any questions, please submit them in the question box off in the dashboard, and we'll kind of try and aggregate everything and send them over to Shannon here. Shannon, let's start with a couple easy questions, I guess. So, there have been several questions about thermal stability and cost of the electrolyzers. Is this something that the cost is close to being industrially applicable, or is this, like you mentioned, for like dialysis where cost really isn't an issue here?
Yeah, Yeah, of course. Yeah, so we haven't done any, detailed cost modeling in part because these things need to be informed by lifetime and durability, and those are the hardest things to measure. So you can do all the cost modeling you want, but if you don't know how long it's going to last, then it's sort of useless. But we can talk about it at a high level. So I'll talk about it at a high level. So what does this entail? It entails that you basically have two membranes instead of one, right? Because we're going to have a bipolar membrane. So there's an additional materials cost. I think can be substantial. For example, Nafion is actually a pretty expensive proton exchange membrane material. It's one of the big costs in electrolyzer in terms of materials budget. But there are lots of other membrane materials that can be used, and it depends on the application. Now, so that's sort of the CapEx upfront costs. Now, assuming we can get good durability, I don't see any reason why the durability can't match that of the monopolar membranes. There's these inorganic particles in the junction. They should be thermodynamically stable in the conditions if we choose the right ones and tune them. So I don't see any reason. We have run these for a long time, days, and they do degrade. We don't understand why, but they degrade slowly. But a lot of the monopolar membranes do as well, particularly the alkaline exchange ion membranes. So those sort of commercialization and improvement of those will naturally lead into better bipolar membranes. Then the big question is OpEx, operating expenses. So that gets into the durability and the efficiency of the water dissociation process. Now, right now, we can run at a few hundred milliamps per centimeter squared in a bipolar membrane and lose only maybe 100 millivolts of voltage compared to a monopolar membrane. That's pretty darn good, okay? And in fact, if you're doing something like I showed you, this electrolyzer, if you're comparing to an alkaline electrolyzer where you have other losses elsewhere in the cell, they can actually balance out and sort of give you a equivalent performance. Now, I don't see any reason why we can't improve the performance of the bipolar membrane another 10x in terms of the voltage performance, because we've just started thinking carefully about what goes on in these junctions. So I think eventually the electrical performance will be similar to the monopolar membranes, and then it will become sort of what value add do you have, and then it becomes a question of the application. So maybe there doesn't end up being any real application in electrolysis. I think that's likely. Electrolysis of water, because there are advanced technologies that are well developed, but CO2 electrolysis, you simply can't do what we want to do, what folks want to do with a monopolar membrane. It just doesn't work very well. So the bipolar membranes add a huge value add and will in fact lower the cost of the overall system. Similarly, if you want to make acid and base for CO2 capture and these sorts of things, you just can't do it with the monopolar membrane. So you need the bipolar membrane, and then it's just a question of cost and performance. And I think there's a really bright future for here, but it is going to take some research and development.
Thank you. So there have been a few different questions kind of about what's really happening at the interface and with respect to mechanical stability. So can you talk a little bit more about, you showed some nice reference work about the 3D interfaces. You showed SEM images, cross-sectional of kind of some delamination maybe at that interface. Then addition of these nanoparticulate materials, right? The adhesion of those particles and the adhesion of those interfaces, that's all going to be critical to making sure that you don't have any gaps and making sure that you can continue to function.
Yep.
And then, could you also maybe speak about pressure? Have you looked at higher pressures for these interfaces, which may also in turn benefit the water loss at the interface and the dehydration?
Yeah, so there's a number of things there. They're all important. We haven't looked at them all in detail, but I'll say a few things. So one of the reasons that we have been able to actually make some progress here, and it's almost serendipity, is like I mentioned at the beginning, many people, the vast majority of the field studies bipolar membranes that are sort of sitting between two electrolyte solutions, because that's sort of the geometry you'd have them in an electrodialysis system where there's a big application. So you don't have any static pressure on it. And so a lot of the bipolar membranes, a lot of thought is paid into sort of adhering them together. And there's a lot of additives put to the junction to make that happen. And I'm sure the people at Fumatech, they have this all probably trade secrets, how they keep those things really robust and stuck together. And what we did is we eliminated all that so we could study the physics. Actually, it was not that was the only reason we got rid of. We wanted to keep things as simple as possible, and then we kept it under static pressure. So in an electrolyzer in the MEA type geometry. And I think you could build an electrodialysis system that actually did this as well. The whole thing's under static pressure, you know, and we bolt that thing down. We actually optimize the pressure so we get under as high a pressure as we can get it before it sort of fails and shorts internally and things like that. And those are things that have been optimized in the electrolysis industry for a long time. And so, you know, what happens at the junction at that point? Well, we have all these particles. Oops, lost my pen here. We have all these particles. Is it going to let me write? What's going on here? We have all these particles at the junction, and those particles, and here we go. And those particles, you know, are gonna sort of interpenetrate. You know, this whole thing's under pressure. This is soft material, right? And so I have a feeling that there's lots of corrugation that starts to develop. And then when we cross-section this, it's really hard to cross-section these and get high-resolution images. You know, what I showed you was like a freeze fracture snap. And that works, but you know, you can't tell, like you see delaminate, because you know, just the snapping causes delamination, things like that. So we've gone back and are trying to do very careful microtoming and environmental SEM and plasma cryogenic fibbing and various techniques to get at really that question. But I think there's a lot of complexity at the junction. I think it's not represented by these perfect planar things that I showed you. I think that the mechanical pressure is really key, and continuing to optimize and understand that is important. And I think we still have a lot to learn.
So we've had a few questions about, you know, understanding what's the best catalyst to put at that interface, right? So you've chosen to put oxides there at that interface. You know, question, can you put molecular catalysts there? You know, you know, I mean, my background, I come from kind of the Norskov models of looking at optimization for catalysts. You've talked about using PZC, point of zero charge, as kind of a metric for looking at this. You know, how does that mesh with other traditional or other more classical ways of looking at catalyst efficiencies? Could you speak to that for a minute?
Yeah, it's something we're thinking a lot about. We don't have the answers yet, but I'll tell you what we're thinking about. You can certainly put molecular catalysts. People have done some of that. That was the original work by Simons. They sort of have modified the end groups on the polymer membrane themselves, and you know, looked at proton transfer models for those end groups, because you know, you can have acidic or basic end groups there. People have put a lot of different polymers in the junctions, and none of them work very well. You know, what's interesting is it seems like these heterogeneous oxide surfaces work far superior to anything molecular and discrete. So why would that be? Well, one thing, when you have an oxide surface, right, you have very closely coupled hydroxide. I mean, you know, the acid base sites are extremely strongly coupled. You know, and that's in fact why you see, I mean, if in this titration curve, when I measure sort of, you know, H plus consumption, or when Haukun does versus pH, and you see these curves, they don't look like a molecule would look like that, right, as a single pKa. We actually get a straight line almost. And that's because there's really strong interaction between every single one of these groups. As soon as you deprotonate one, it makes the next one harder to deprotonate thermodynamically because of the interactions. And so, you know, these can exchange protons. Protons can hop around the surface. I have a feeling there's something to do with that that's leading to the much higher rates of water dissociation, but I do not yet understand it. So we have a theory collaborator, Chris Hendon here at Oregon. He has a really talented student, Josh Davis. We're doing sort of molecular simulations using sort of advanced methods to look with implicit water at how does the reaction coordinate look when you pull apart a proton and hydroxide, you dissociate water on these surfaces. So I think that's one of the outcomes from some of our studies now, is a more insight into how to design things, because we have a 0th order model, okay, and we need to get more complexity here and understand it better. So that's a good challenge for folks out there listening. If you're looking for research projects going on in your career, this is a really interesting and rich area that is not well understood.
Interesting question about what are the best complementary techniques for actually understanding and studying these interfaces, right?
Well, I can tell you what we're doing. I mean, you got to get light or some sort of spectroscopic probe in there. So I had a slide on that, but I took it out because the talk was too long. So you know, so we're doing things, kind of obvious things. Tom Maluk has done some nice work recently as a Nature Chemistry paper on this. You know, so you can shine light in and say you have a pH sensitive molecule that you can put in the membrane junction. you can measure under different bias and things like that how the pH at that location evolves if you can get photons in and photons out to probe that molecule. So that's one of the things we're trying to do. Say you want to probe electric field. Well, there's been a ton of work probing electric fields in biological systems. People use Stark shifts, vibration or optical Stark probes to do that. And so that's another thing we're trying to do. It's this very obvious thing. But again, how exactly you build the device and get the light in and out and get enough signal, right? Especially when you have scattering particles at the interface, it's not a trivial technical experiment, but those are some of the things we're working on. We're also looking at, operando X-ray absorption spectroscopies and things like that to see if we can actually see structural changes as a function of bias and things like that. So we're sort of putting all the standard tools you would use to try to do this. And if anybody has any suggestions on easier experiments, let me know, or go do it yourself and send us your paper to review or something. We'd love to see it.
Maybe time for another one or two questions. Some questions about kind of what can be used aside from just pure water. So how well does this translate to CO2? How dirty can the waters be that you're using in these systems? A little bit more about that, if you would.
Well, certainly, industrially, we haven't tested in many of those things, but industrial, a lot of the applications involve, complicated waste streams. So, for example, you might want to pull a precious metal cation out or precipitate it, or do some cleanup on a waste stream. So they can in principle be fairly robust in those conditions. A lot of that has to do with how the membranes are designed and the lifetime you expect. You expect them to last a month, a year, a decade. So that's a lot of engineering things that I don't have good answers to. We've primarily looked at pure water systems, because primarily, although we are certainly interested in the applications, and we're primarily trying to understand the underlying physics and chemistry, and so we try to simplify. But there's a lot of opportunity there. One of the things that I find quite interesting about these systems is just the practical reality that this large flux of ions that's coming out of this membrane when you're operating it really does dramatically change how other species are transported. And so we wrote a perspective about this. We talk a little bit about this. You can read it in Joule. My graduate student, Grace Lindquist, she wrote this beautiful article, and she kind of proposes that maybe these are going to be useful for these sort of dirty water or seawater electrolysis, or simply more robust electrolysis systems that are sort of more tolerant to those impurities. But again, this is early in that area. There hasn't been really anything out there systematically looking at this. That's one of the things we're doing in one of our collaborations. So Tom Jaramillo's group's actually going to be starting to look at some of this stuff. They are right now doing that, so we expect to have some more results soon.
Great. Well, Shannon, I think we've pushed you through a lot of questions here. We're just at the end. I wanted to thank you for jumping in to give our first presentation here. Very interesting work that you've got going up there. Good to see that you have so many different students working on these projects. Want to thank you again and thank everybody for attending. If your question wasn't answered in our specific Q&A session, we're going to try and get answers out to you afterward. We'll see if we can manage everybody's email and everything through the platform here. But if you do have standing questions, feel free to send them over to BioLogic or to Shannon, and we'll do our best to get answers to you.
Absolutely.
Shannon, thanks very much, and we'll talk to everybody again soon.
Yeah, and I should mention that all these measurements are done with BioLogic instrumentation, just so you guys know. And we got a lot of high quality data from our BioLogic instruments that we're very happy with. So thank you, Arnold, for the invitation to give this seminar. Of course, it's always great to be able to talk about our work.
Great, thanks, Shannon, appreciate it. Have a good day, everybody. Bye-bye.
Bye.